All right, good morning, everyone, and thank you all for joining. My name is Hammond Pierce, and during this year's Hack3D competition, my role is as the lead judge and competition supervisor. Judging with me and also on the panel today are Professor Nikhil Gupta, who was also the faculty organizer of this competition, and Gary Mack, who was also the main competition organizer. This is the third year of the Hack3D competition, which has the general purpose of raising awareness of the intersection of cybersecurity and manufacturing, especially within the domains of reverse engineering and product counterfeiting. This field is becoming really important as the additive manufacturing industry is expanding worldwide, and it has a complex digital supply chain which accompanies its real-world physical supply chain. This year, competitors were asked to first complete a qualifying round where they needed to reverse engineer a light bulb based on incomplete information. 4 teams completed this challenge and proceeded to this final, where they were challenged to both find the stress in a given part based on incomplete simulation data and to recreate the model of that same part. In order to complete these challenges, competitors have had to employ skills in graphics programming, file manipulation, and advanced part modeling. Each team today will have 10 minutes to present their solution, and then there will be an open Q&A at the end with all the teams, where you, as the audience, can write in questions using Zoom's Q&A tool. Once these presentations and the Q&A have concluded, the teams will be invited to a private discussion with the judges, and finally, the winner will be announced in Sunday's Global Award ceremony. Before we begin, I'd also like to thank the following: the summer research students Angela, Johnny, Caleb, and Phoebe from NYU and City Tech, who helped develop the Hack3D challenges that were given to the competitors this year. I would also like to thank the National Science Foundation for funding this competition, and the Seesaw organizers, Ramesh Kari and the NYU Center for Cybersecurity for hosting us. And I would also like to thank our partners in Hack3D and other additive manufacturing security events, the New York City College of Technology. I will now hand over to the lead competition organizer, Gary Mack, who will discuss this year's challenges in further detail, and then we will move on to the team presentations, starting with Team DC War Story.
Thank you, Hama, for the introduction. Good morning, everyone. My name is Gary, and I am one of the main coordinator for the Hack3D competition. I'm currently a second-year PhD under Professor Nikhil Gupta's laboratory, and my research mainly focuses on cybersecurity and additive manufacturing supply chain. And for this year's Hack3D competition, I will share my screen here. I want to talk about the qualifying round challenge that we've created. Every year in the summer, NYU has a summer research program where many departments open up and students can register and work on the research project in the summer. And in this year's summer research program, our summer students have come up and developed this qualifying round challenge. As you can see on the screen, this is a light bulb, and what we have done is we have taken the solid bodies and all of the geometry and completely stripped out of the design. And we replaced it with these curves, these 3D curves that represents the silhouette of the light bulb design. And the challenge here is to have the participants reverse engineer the light bulb based on this, this information that is given to them. And also, we've incorporated elements of mechanical engineering for reverse engineering, as well as computer science, where we've used certain codes to implement into our design. One example would be in the light bulb filament, there is a code injected in there because that area shows no cross-section area. So based on all of these different file forensic techniques, students will have to try to come up with a solution and redesign or design the light bulb CAD file and provide that back for us. In the qualifying round challenge, we have over 40 teams that participated in the qualifying round. And I have to take a moment to congratulate all 4 teams that made it to the Hack3D finalists. We have participants from all over the world, and Team Cobra from NYU Tandon School of Engineering, Blue Hens from the University of Delaware, Team Fleck from National Institute of Technology, Karnataka, India, as well as DC War Story from Malavinaka Institute, National Institute of Technology, also from India. These 4 teams will have 10 minutes to present their final challenge solution. And a brief summary of the final challenge. What was done here is we've taken a part and ran a simulation study on the model. And we've exported the simulation study as a VRML file. If you're not familiar with a VRML file, it's a virtual reality modeling language. And it can be viewed in a viewer as well as open up in a text editor. And the challenge here is to be able to determine the maximum stress from the VRML file, which there is a lot of information that's not given within the file, as well as you'll see later on in the presentation, for this design, this brick design, in the interior bottom, it's missing some features. So students will have to analyze the files and determine and recreate and redesign the interior features to allow these bricks to stack on top of each other. So there's 2 tasks. One is reverse engineering and to be able to determine the maximum stress from the part. And with that said, I'll now like to pass it over to our first team who will be presenting today, and that is Team DC War Story. So we have Devesh and Charyu.
Thank you, Gary. I'll take over. I'm Chirayu Rankawat. I'm a part of DC War Story. We are a team of 2, Devansh, Kirk, and me. First of all, I'd like to thank everybody. We are delighted to be part of the final round of this challenge. And I'll move on to the problem statement. So as Gary mentioned, we are provided with a mesh file. It's a deformed part. It's a brick, a deformed brick on which a simulation study was run, a static simulation. The mesh file and a reference JPEG file along with the legend of this simulation stress distribution as well as the numerical scale were provided. However, no units were disclosed. The study performed was to simulate the stresses experienced by the brick when stepped on by an adult. This photo is the reference JPEG file which we received. We are asked to reconstruct the brick close to the original file dimensions, which can stack on top of each other, which is its function, and gather the simulation data from the reconstructed file with the max units, max stress and units. So the VRML mesh file we received carried information of stress in form of physical deformation and the color map on the surface. We also found 2 alphanumeric codes on the underside of the brick of the mesh file, which we received. These codes were later, we kept these for later so as to analyze them later, as we couldn't find any significance at the moment. The reference JPEG file provided a legend with the numbers. So pixel scaling the legend allowed us I mean, like pixel scaling, legend gave us the max value, which was about 90 units. The units were yet to be determined using simulation. So we began with the reverse engineering of the model. So the given VRM mesh file was uh, chosen. We opened the mesh file in a CAD software. We followed through using elemental length summation to find the width, length, and the height of the brick. We used the points of the 3D mesh where least deformation was observed, and the elemental length summation method was to basically add this node distances between the uh, distance between the nodes of the mesh, and to sum them up so as to get an idea of the value, because we expected an error, but that error would have been very small because our point of calculation was where the deformation was expected the least, which is at the base of the brick. And for calculating the height, we use the vertex on the corner, which also observes the least deformation and displacement. Uh, and then a major challenge was to find the radius of the studs on top of the brick. Um, because the deformation resulted uh, in the studs, uh, gave them an electrical shape. Uh, it was a challenge to find the exact value. So we observed that the corner studs had an ovalish deformation and was not uh, an accurate place to find the circular radius from that deformation. So we relied on the studs close to the center of the brick. We constructed a reference plane on top of the elliptical deformation, and because the stress close to the center was causing the studs in the middle to deform only on one axis, which we then describe as a major axis of the formation formed ellipse. We relied on the major and minor axis considerations of the ellipse formed, and then consider the ellipse so minor axis, which led us to an accurate value of about 2.4 radius of the stud. And because we were uh, expecting a slight error in that method, we also took a mean value method to identify the radius of the deformed ellipse. So the mean value was identified as with the same reference plane that we use uh, to find the minor axis length of the ellipse. Instead of uh, uh, producing a ellipse on that part, we used a circular we shaped circular features on top of it, and then we averaged the radius formed by those circles, which also came close to the elliptical method value, which was about 2.4 features that we had to make relied on the stacking mechanism of the brick. So the stacking once the stud diameter was found, it was easy. We used the elemental summation method to find the distance between the wall and the stud center as well. and also the distance between the two studs. Once these lengths were identified, stacking mechanism was a method to do the stacking mechanism was formulated, in which we describe the length from the wall to the stud center as half of that of distance between the two studs in the brick. And the we then proceeded to look into multiple methods of stacking. We noticed that the shell thickness during the measurements of the brick was about 1.2 mm, which meant that the interior of the walls of the brick, when stacked together, did not make contact with the studs. So it meant that we had to do some kind of projections to solve that issue. So we had two ideas in mind. We had a tubular extrusion underneath the brick, which extended between the four studs and provided contact between the studs and the brick on top. Or we add projections on the interior walls, which make contact with the bricks studs beneath. So because we are not able to identify or close down on one single brick, we took multiple cases, and we were going to validate each of these cases using our simulation study analysis. So the brick was identified. The outer shell of the brick was identified because the interior features were yet to be confirmed. So these were the dimensions we found. And so the length is as shown. Start radius was 2.4 mm. Distance between the two studs was about 8 mm. The tube construction was taken on a basic approximation because we only had the outer value, and the inner value was deciding factor for the thickness of the tube. Now, because we weren't sure about the structure and its validation, its validity, we decided to keep it varying until we find a proper validation to verify our proposed model. The stacking mechanism was used, as I explained before. The tube structure makes contact with the studs on of the brick beneath and causing friction. And we'll move on to simulation study. So once the bricks specifications were derived, we proceeded on to the simulation study. It was given that the simulation was run on the brick with consideration of an adult applying or stepping onto the brick. So we found one of the constraints given in the problem statement. But during our determination of constraints, we did some research, and according to the study, we found that research. It stated that the weight of a person, weight of an adult, is not the exact force applied by the person while in motion. Basically, it suggested that the instantaneous force applied by an adult onto the ground is about 1.25x the time times the weight of the adult. So this study helped us to identify a range of the input forces to apply. We took the average weight. We took the average weight as about 190 pounds, and taking the study into consideration, we had a input force of about 230 pounds. So this was one of our constraints. Second constraint was about to match our legend, the scale of the simulation study, the numeric scale, the numeric value produced by the study to match it with the reference JPEG file we were given. Another constraint, not constraint per se, but provided, let's say, provided a finite number of cases to work with was units across CAD softwares, multiple CAD softwares were uniform. There were about 5 units: PSI, KSI, bar, megapascal, Pascal. So this allowed us to determine the number of sets of iterations we had to go across each proposed model we had. The deformation was not of true scale in the given VRML mesh file, which is something we found out by producing our own mesh file, so as to figure out figure out more information. And we found that the mesh file produced was may not be of true scale. We were not sure as to whether the mesh file was of true scale or not. And this process helped us identify the mesh file was not of true scale. This was further verified using the input force and matching the numeric scale of the legend. So each of these forces, we converted the legend produced by each of these simulations into the said units and try to match the scale provided and our simulation study scale, and compare the force values which were required to attain those scales on our simulation. And we found that the force required in each case was varying by a lot of magnitude. KSI was requiring about 1,400 pounds of force to produce a similar legend. When using a bar scale, we found the force to be about 300 newtons to produce a similar legend. PSI required us to use a 2-pound force to produce a similar legend, which was obviously not close to the adult force applied onto a brick. However, we were able to identify that megapascal was the right unit and helped us produce the right legend, which was comparable. We were able to identify the units, but we still did not have the confirmation of which model was the right choice. So identification of the units helped us to then start. Identification of units itself became another constraint for us, and then helped us further identify which model was the right choice for us. So because the deformation was of not true scale, we had to assume that it was a custom or an automatic scale. But it was noted that the behavior of the surface, the top surface of the brick and the studs, the shear produced and the behavior and the direction was an important point, which meant that we could utilize the area of maximum stress, or you could utilize the shear produced on the stud, and use that relative geometry as an identification method. However, not accurate, but this was the only constraint we had left to work with. So this information was utilized to isolate our final model. So we ran multiple cases with grooves, with ribs on the tubular sections. But these cases were neglected or ignored for the following reasons. On the presentation you see is a ribbed model in which we made a rib across the middle section of the brick to provide support, essentially. But if we notice that the stress deformation of that brick on the right side shows that it is very directionally opposite and asymmetrical when compared to the original mesh file which was given to us. Bricks with the grooves on the interior side of the wall was neglected because the maximum stress came on the interior section of the wall. This stress behavior then led us to believe that the grooves was not the right method to approach with. Because we've neglected the ribs and the grooves on the internal section of the wall, we were only left with the tubular section on the inside of the brick. And we decided that this model was the right verified model based on our constraints, which we followed. The final part dimensions were as follows, and that's it from our part. Thank you.
Great, thank you so much for Team DC War Story for their presentation on the Founding Challenge. We'll take a brief moment, and next we will have Team Fleck, which will have 10 minutes to present. And
Hi, Gary, can I start?
yes, whenever you're ready.
Yes, please.
Okay, good. That's good. So very good morning to all of the judges who are here and the organizers, and to all of the other teams and attendees as well. We are Team Fleck. We are a student team from National Institute of Technology, Karnataka. It's an engineering college in India. So the CSAW Hack3D finalist competition was divided into two parts by the organizers. So there was task 1 and task 2. We managed to finish both of the tasks successfully, and we will be presenting them to you sequentially. So the first task was to modify the 4x2 WRL file that we received and recreate it to allow it to be able to stack on top of each other like a normal Lego brick would do. So for this, we have followed 5 steps. The 5 steps were in the next slide. We rendered the WRL file, and we identified the important features, that is displaying the file and getting to know how it looks. And then we analyzed the model for the dimensions of the WRL file. We obtained standard parameters that are available online for actual Lego pieces. We built a stackable 4x2 brick in Fusion 360 based on the online files that we got from the internet on a standard Lego piece. And then we matched our built model with the WRL file to ensure that our file matched the WRL file that the organizer sent and that it was accurate. So this will be presented in more detail by my teammate, Chandan.
Good morning. Coming to model, reconstructing the model, we got a WRL file. Using the WRL file, we went with different approaches. We used the Cortana 3D tool. We are able to view it. And coming to other tool, it's a 3D view plugin to Google Chrome. Using that, we came up with viewing the model, which is actually deformed, and we export it as a STL. Next slide, please. This is the file which we are able to view using a 3D view tool online. And coming to that, we have exported this file as a STL. Next slide, please. We are able to view it in other tool, which is a 3D tool, View version 14, which will give the solid model, which we can make it an object file or STL file as well, which helped in for figuring out the dimensions approximately matching with the standard model 4 into Lego brick, so that we came up with the standard model, confirming that we're dealing with the model. Next slide, please. This is the model which we are able to do view using our 3D tool version 14, which came up with, we came up with the interior features which we are able to view, and there are some missing features also. We came up with in the next slide. Okay, next slide, please. Okay, these are the dimensions which we are able to confirming ourselves that we are dealing with the 4 into 2 Lego piece with some missing interior features, and those dimensions in mm. Next slide, please. We got an STL file which we got an STL file which is open in Fusion 360, which is used further for creating the model. Next slide, please. Okay, using that file, we reconstructed the Fusion 360 model, a model in Fusion 360, which have more than 50K faces. Next slide, please. From that, we are able to make the model.
Brownie points to you for being so well-rounded, but I seem to have
I'm not sure what happened. So we imported the mesh file. It had over 50,000 meshes. So we had to join the meshes together, merge them, and then smooth it over so that the analysis could be conducted later on. We found 2 ways of doing this. The first was just merging the faces manually, and the second was exporting it as an object file and then converting it to IGS, which would give the same result, which we did. In the next file, you can see next slide. This was our final result. That after constructing it in Fusion 360, we managed to construct the interior cylinders that allow it to stack on top of each other, and we managed to solve the deformation so that it looks like a normal Lego brick. The dimensions for this were matching those that are matching of a normal Lego brick, and they match the WRL file as well. So in the next slide, you can see the reference schematic that was used to develop the Lego brick. These, as we have confirmed earlier, we cross-check these references with the WRL file set to make sure that they are accurate, and we have adjusted the values accordingly. After this, we had to solve the task 1, and we had a stackable Lego brick, 4x2 brick. So now we moved on to the next task, which was to determine the maximum stress that was caused when simulating the brick by the organizers. So for this task, I think it was my colleague Hassan will present this task.
Good evening, everyone. So after task one, we have different CAD models for the given WRL files. We analyzed those files using ANSYS Mechanical to get the final stress model. We applied a force of 175 pounds, which is an average human weight. But later on, we adjusted it. Uh, using the limits and the conditions which we are facing. For the material, we tried different kind of materials and when while doing the simulation, uh, we observed the deformations which we encountered. So among all the materials, the result with the ABS was most closest to the given conditions. Moving next, as mentioned in the slide, we used standard values for the tensile stress for ABS, that is 6100 psi. For this data, the value varied from 2 kilo psi to 7 psi, but we used this value for as an average, and for Poisson ratio we use 0.35. Uh, we analyzed different kind of models. So we had we have taken dimension from the WRL file, and then we tried different tubes and different combinations for getting the missing CAD features. Uh, we for taking like for taking the tube diameter, we used the space between the studs at the top, and we simulated with different tube radius so as to obtain the stress results closer to the given value. We also tried different other methods besides using tubes, but the results were not similar to the final value, so we skipped those. Moving next, we used a maximum possible mesh which was available for the given license under ANSYS to us. So we used the element size mesh division. We could have used the spherical division, but since the force which was being applied was perpendicular and surface and it could have been uniform at any particular position, so we went with the elemental size. The size of element was 0.5. uh, uh, the force which was applied on the top was 177.5 pound, as mentioned earlier. It was applied particular to the top face towards the ground, which is negative z axis in this case. Moving next, we fixed for limiting conditions, we fixed the bottom of the Lego brick, considering it to be placed on the ground, while the tubes we allowed them to move in a particular direction uh, because the tubes were shorter than slightly above than the ground than the lower part. Uh, so when the force was applied onto the brick, the tubes moved up to certain distance, which is 0.20 uh, in uh, in this case, and after the touching the ground, the stress was distributed along the whole brick body. So we ran this test on different types of models. We also tried this with a CAD feature with the no CAD feature model also. So the results we got for that particular model was maximum equivalent stress of 116 psi, which was at the center, while at the bottom of the stud, which was mentioned at in the JPEG file to derive, it was not our maximum stress, but the value which we got there was closer to 90s, between ranges of 88 to 101. So for an average value, we have taken 90 psi stress for that position. Moving next, we tried the similar feature with the different type of models, as mentioned earlier, that with single tube in the center, or with the two tubes at the two ends. We used ribs also, and we applied different features. And two of the results are shown here. as you can see in the diagram, the deformations were for tubes were closer to the final result, but as in this case for two tubes and single tubes, these were not as close to the result as it should have been. So but for three tube condition, as in the next slide, you can see the results were the deformation which were introduced were quite similar. Uh, but the problem which we faced here was that for 177.5 pounds, so the weight, human weight which we are using, the legends or the value limits which we are getting was not accurate. Also the deformations were not according to the final result. So we adjusted that value, as you can see in the next slide in the video, that when applied with uh, human weight, uh, the stress deformations were not as required.
Hello, Hassan. Sorry to
Okay.
interrupt. I'm going to have to ask you to sum it up within the final minute so we can have equal time for the other finalist teams. Thank you so much.
Okay.
Your presentation.
Okay. So yeah, thank you. Yeah, so I'll finish it quickly. So as you can see that for the stress values were not limited, not we didn't get the proper deformation value for the final model. So we reduced the stress value, the applied force value to 30 pounds to like we used different values, but the most appropriate result which you got was around 30 pounds. So we used 30 pounds for generating that given video, and we generated the final model with that. So when we calculated this, the maximum equivalent stress which we got in this case was 196.97 psi, which was at the intersection of top of the brick and the top of the tube, whereas the maximum the stress which we got at the bottom of the stress was around 90 psi. So that's our submission. Okay.
Thank you. So the final result was 90 psi, and the overall break had 196 psi, as Hassan mentioned. And this is our team, and that's us. And finally, thank you for listening to us. Yeah, thank you to all the judges and organizers for this awesome competition. That's it. Over to you, Gary.
Thank you, Team Fleck, for the presentation. Next, we have Team Cobra, who will be presenting their findings for the final challenge. Team Cobra, whenever you're ready, you can share your screen and start.
Hi, I'm Tarun. I'm representing Team Cobra today. So our first task was to reconstruct the model from the information that we had, the WR file. And we had done the CAD modeling with the standard Lego brick, since it was mentioned more than once that it was a Lego brick that was taken. So we didn't want to make many assumptions, but we got the exact Lego dimensions and kind of added the cylinders to make it stackable and the standard Lego dimensions. And we realized that when we checked the dimensions of the deformed file and the Lego brick in Ultimaker Cura, we found out that the error between these two was only 6%, and we assumed that that was because of the deformation of the GIMP file. Now, the next part, the most important part of this thing, was the maximum stress value and the dimensions of the value. We were not to make any assumptions, so directly went ahead with trying to find out everything we could from the given data. So the engraving in the bottom had a line number that was mentioned. When we went and checked the line number in the WR file, when we opened Notepad++, we found out that the following lines were written there. So we converted this what looked like a binary value into decimal and then tried to look for how it could relate to it. And then we found out it had direct relation to ASCII coding. So when we deciphered it, this is what it showed. Special character, 91 directly translates as special character, 77 as a capital M, 80 as P, and 97 as small a. So since special characters doesn't really fit into the whole setting, we decided that it was 91 megapascal. Just to be sure about it, we also checked our we also checked out the we assumed a linear relation of the given image, and we tried to find out the length of, I mean, we're trying to find out the maximum value based off what we could over here. And it was pretty close to the value that we deciphered, which was 50.59 was what we found out from the image processing, and 91 megapascal was what we found out from deciphering. And again, there is no way we could find out the the units from this method. So the deciphering was the right way to go about it for this part. Now, Dave will take over for a bit.
Good morning. So I would like to go back to the first slide just to reiterate a couple of points. So as we ended up performing the reconstruction of the brick, initially we imported the given file, the given VRML file, into Ultimaker Cura, as Tarun mentioned. And that gave us these three dimensions that was basically the dimensions of the bounding box that surrounded the particular STL file. And the way we converted the VRML file to an STL file was using an online open source converter. Next slide, please. So as you can see at the left there in the image, that's basically the same thing that's done for the reconstructed brick. And we actually went over a couple of iterations of modeling our brick. So we used different dimensions, very close to what we saw with the bounding box that was generated with the given deformed VRML file. And as we did that, we came at a point where the bounding box is very similar to the one that the deformed part generated. And when we cross-checked with the actual standard dimensions of a Lego brick, we found that the Lego brick's bounding box is very close to the VRML file's bounding box. Next slide, please. So this particular phase of the process also gave us another numeric code at the bottom, which was 2-252. And it is our assumption that the 2-252 could hint towards the part being a Lego brick, because we actually ended up researching more about this, and all of the Lego bricks, especially the original Lego bricks, have a mold number at the bottom of them. So this particular number corresponds to the injection mold that the brick was made in, and also follows a similar pattern with a number followed by a dash, and then the remaining of the number. So that basically gives the company an indication of where the brick was made and which mold was used to make the brick, in case of some sort of an error in the manufacturing process where they could recall the whole stack if there was something wrong. And we just thought that it was a clue hinting towards the part being a Lego brick. Apart from the other alphanumeric that was already provided, as you can see on screen, the L38564. Yeah, and that's about it. So we also didn't want to make an assumption with any sort of simulation data, even though we did perform a simulation. We performed the simulation based on the scale that was given in the image. And if you look at the next slide, you have that scale here. We basically use 91 megapascals, 91 pascals, 91 psi in the ANSYS simulation. Now, however, looking at the image, it's very hard to say as to where the stress is applied. So we tried applying stresses over the cylindrical faces on the top, and also on the flat face, just a plane below that cylindrical face. And we believe that as the task indicated that the value and the unit of the stress was the most important aspect, we didn't want to make an assumption as to where the stress was being applied. And also the other way we tried to do it was actually adding a weight to the brick to try to see if we can get to 91. But again, we found that method to be a little inconsistent because it is a little hard to generalize the weight of an individual, given that we have no idea where the individual is. So it's very hard to make an assumption of weight based on no information about the population. So we just ended up sticking with the method of deciphering the VRML file. And I would like to conclude by saying the values that we derived from the scale bar was less than 1% away from the actual value that we found in the VRML file. Thank you so much.
Thank you once again for Team Cobra presenting their final challenge solution. Next up, we have Team Blue Hens. So whenever you are ready.
Okay, thank you for having us today. All right. Okay, so my name is Nicholas Cater. I'm from the University of Delaware, and myself, along with Michael Hutz, make up Team Blue Hens. So to tackle the first part of the problem, we opted to recreate the CAD file from scratch. And the first thing that we needed to do was we needed to determine what the dimensions of the brick were going to be. So to achieve this, what we did was we opened the WRL file in FreeCAD, and we used the measuring tool to find the dimensions of the file that was provided to us. So when we found the measurements, we found it to be 31.75 millimeters by 15.81 millimeters by 9.55 millimeters. And what we did is we did some research and we compared this to to Lego's official specifications for the brick dimensions. Lego's official specifications were 31.8 by 15.8 by 9.6 millimeters. And so based on the correlation between the dimensions we found versus the ones we researched, we confirmed it to be a match. And so because of this, we opted to use Lego specifications for redesigning the brick. And we did some research and we found that this helpful blueprint that detailed the basically the interior and exterior measurements of the Lego brick. And this is what we used as our inspiration for designing the CAD model. So once we had found this blueprint, we were able to use the numbers and the measurements that were listed in it to design our own brick. So what we did is we opened it up in Fusion 360, and we, based on the specifications that we researched from the official Lego blueprint, this is the model we came up with. And you'll note the 3 cylinders on the interior of the CAD model. And once we were able to implement all the specifications from the Lego blueprint, we were able to advance on to the next part of the problem, which was determining the max stress unit. So for this, I'll pass it over to my teammate, Michael Hutz, to comment on this.
Okay, thank you, Nick. So as you can see, the way we went about determining the max stress value was initially we just used the information given from the stress test.jpg, which ended up being, as we analyze it, rather accurate. So using simple pixel counting, we could find that the distance between points could kind of give us an idea of the maximum values quite easily. We found that about what 1 pixel is equal to about 0.19 of whatever the units of stress on the legend might be, which we later found the stress units. And from that, we could then find the total max unitless, which was 90.3. Oops. So a key thing we did was, since we had initially found the max value according to the image, we weren't absolutely confident that the file we were given was going to correlate with the simulation. We didn't take that as a guarantee that the absolute maximum point would match the exported file. So thankfully, the file was completely readable in plain text. And from there, we could look at the color data and confirm that we had matches in the file, which there were. Specifically, there were 2 points in it that used a fully red point, which if it's 1, 0, 0, that means it is the maximum, or in other words, matching the legend maximum of fully red. And with that, we found 2 indexes where it was confirmed to be fully red. So we from there knew that that value we initially found through pixel counting was actually representative of the file. There was a few more key clues we found in the file. Specifically, we found a few comments in the file referring to von Mises' stress max. We sadly were not able to draw any conclusions from that information, but we took it as some sort of red herring to the result, since it was not at a point that was the maximum, but instead a quite non-max point. This was just assumed to be a red herring. Okay, so based on what we had in the listed color area, and the fact that it was in the coordinate index, we just want to, or excuse me, the fact that we had the color was true, but we again weren't absolutely confident that the data we had was totally accurate. It could have been obfuscated in some way, including additional colors or additional anything. There was no guarantee that what we had was accurate. So we, again, using the Excel file I found, verified that the indices we found of the colors were actually appearing in the coordinate index, which the coordinate index indicates with the color, if I can pull that up, the color index correlates with the coordinate index to specify what color specific point should be. So at this point, we had verified that the specific unitless value we had seemed to be correct, but it was not entirely clear what the value should be. So we knew for a fact from the description that we were dealing with a human adult stepping on a 2x4 brick, which we assumed the average human to be about 70 kilograms, and did a more basic, quite basic simulation to find just a key of what the unit might be. And given what we found from our simulation, we found the unit to be kilopascal, and therefore we could conclude from that that the max pressure on the brick, the max value was 90.3 kilopascal. And I believe with that, yeah, so that ended up being our final conclusion for the second part. So that concludes our presentation.
Thank you so much for Team Blue Hens for your final presentation. And with that, that concludes all 4 teams finalists have went and presented. I don't see any questions in the Q&A. So if there is any questions from the audience, feel free to enter in the Q&A. We'll take a moment for that. And meanwhile, I'd like to finally thank once again all of the finalist team that made it to the Hack3D final challenge, as well as all of the attendees that are watching in on the Hack3D presentation. The winners will be announced this Sunday in the award ceremony, so stay tuned for that. Okay, we do have one question that came in for Team Blue Hens, and that is in regards how do you decide on the units of kilopascals?
So I guess I'll answer that. So we did a kind of, as we found the that one point and seeing the other presenters were aware that's off by 1,000. I can say that our calculation for that was probably a bit too elementary as far as how we found it, but I wish I had the math we did for it available, but it was a more simplified calculation that put the range as a few thousand Pascal, therefore kilopascal. So it wasn't too complicated how we found it, to be completely honest.
Okay, thank you. We have another question that came in for Team Fleck. Can you explain the STL file generation from your VRML file you have done?
Yes. Am I audible?
Yes.
Okay. Coming to conversion of double oral file to STL file, we use two tools. We approach in 2 ways. One is using the plugin called 3D View and exported that file into STL file. That's simple. And coming to second one, we can obtain object file as well in 3D tool version 4, which is available in online. For maybe it's a licensed one. I guess it can be used for converting or exporting as a STL file or object file. So that we got a STL file from double oral file.
Okay, thank you, Chandan, for that answer. Okay, I don't see any more questions from the Q&A. Professor Gupta, do you have any final remarks?
Yeah, this year, the competition was quite successful. We had more than 40 teams that registered. So being in top 4 means a lot for these teams. I think they did a great job in the preliminary round. And we are excited to see the progress they have made on the final round. These events are geared towards having more focus on the security in the design area, because that is one area that has been lagging for quite some time. So we always rely on cybersecurity professionals to provide security. But these competitions show that as mechanical engineers, there is a lot we can achieve at the design state. So I want to thank finally all the organizers, Hammond, Gary, all the students who took time out and spent numerous hours on designing these challenges, testing them out, and organizing this competition. And we want to thank National Science Foundation for providing funding to run this competition. So thank you very much.